Welcome to our deep dive into the fascinating world of rare earth elements, or REE. You've probably heard about them in the news, especially in the context of technology and international trade. In this video, we will explore the world of rare earths. From their discovery in 1787 to 21st century technology implementations, we will look at the specific elements that are classified as rare earths and which applications and end uses have made them indispensable to modern living. Examining the supply chain of these materials, we find that China has strategically created a dominant position in the mining and processing of REE. This dominance imparts a control lever over global trade and political negotiations. Finally, we will look at the options for alternate sources outside of China as of 2025. The term rare earth elements, or rare earth metals, refers to a group of 17 chemically similar elements in the periodic table. These are the 15 lanthanide series elements, from lanthanum to lutetium, plus scandium and yttrium, which share similar chemical properties but have different electrical and magnetic properties. Despite their misleading name, rare earth elements are not scarce in the Earth's crust, but are called rare because it is very unusual to find them in a pure form, and challenging, expensive, and environmentally hazardous to extract and separate them from other minerals. The chemical properties of rare earth elements are nearly indistinguishable from one another. The first rare earth element, ytterbite, was discovered in 1787 by a Swedish army lieutenant near a village called Ytterby. Early chemists were captivated by the complexity of separating these unusual materials into distinct elements. The intricate chemical separation processes required intensive labor, often taking months. It took more than 100 years for the first significant rare earth industrial product to appear. In the 1890s, chemist Karl Auer von Welsbach developed a mantle made of a mixture of thorium and cerium for use with gas streetlights. More than 5 billion mantles were sold worldwide through the 1930s. It wasn't until the mid-20th century, particularly during and after World War II, that technological needs spurred more substantial industrial applications. One such industrial application that requires these advanced properties is the need for stronger and more thermally resilient and stable permanent magnets. Scientists at Wright-Patterson Air Force Base, in cooperation with the University of Dayton, developed the first rare earth permanent magnet with a formulation of samarium cobalt. Before rare earth magnets, magnetic materials like alnico and ferrites were used, but had limitations in strength and temperature tolerance. REE magnets, on the other hand, deliver much higher magnetic strength, are extremely resistant to demagnetization, operate at higher temperatures, and have excellent corrosion resistance. However, samarium cobalt has limited supply and is expensive and mechanically fragile. The mass-market use of REE magnets would come later with cheaper, stronger, and less mechanically fragile neodymium iron-boron magnets in the 1980s. Today, these magnets are essential components in a vast array of products. They enable the technology behind small power tools and electric motors, printers, headphones, loudspeakers, and magnetic storage. Even the small vibration motors in your phone. Beyond magnets, other rare earths have unique properties that make them indispensable in other sectors. For example, yttrium and europium are used in television and computer screens to produce vibrant colors. In the medical field, rare earths are critical for technologies like laser surgery and MRI and PET scans. The leading United States domestic end use of rare earths was catalysts. Petroleum refining, especially fluid catalytic cracking, is the main industrial process that rare earths are applied. They also find wide application in catalytic converters. Perhaps one of the most sensitive and strategically important rare earth metal applications is in defense technologies. They are used in almost every form of defense technology, from fighter jets like the F-35, which contains over 900 pounds of REE. An Arleigh Burke-class destroyer requires approximately 5,200 pounds, and a Virginia-class submarine uses around 9,200 pounds. REE are found in numerous other mission-critical defense systems, such as guided missiles like the Tomahawk, powerful radar systems, Predator unmanned aerial vehicles, and smart bombs. Now that we understand how crucial rare earth metals are, let's talk about why the global supply chain is so heavily reliant on one country, China. Currently, China mines around 60 to 70% of the world's rare earths, and it processes an astonishing 90 to 92% of the global supply. This near monopoly across the entire value chain, from mining to refining, didn't happen by accident. As far back as 1992, the late Chinese leader Deng Xiaoping famously said, "The Middle East has oil and China has rare earths." Beginning in the late 20th century, China strategically prioritized the development of its rare earth mining and processing capabilities. This was often achieved with lower environmental standards and labor costs compared to other nations. The extraction and processing of rare earths are known to be costly and environmentally polluting. The process often involves the use of solvents that can produce toxic waste. Additionally, many rare earth deposits contain radioactive elements like uranium and thorium, posing further environmental challenges. For many years, Western customers were content to rely on China for these materials, in part because they avoided the environmental consequences of production within their own borders. Over time, China nationalized and consolidated its rare earth mines, bringing the industry under state control. They also invested heavily in building advanced processing and magnet manufacturing facilities. As a result, China now produces about 90% of the world's rare earth magnets. This strategic focus and investment have given China significant control over the rare earth supply chain, a control they have shown they are willing to use to influence geopolitics. In response to tariffs imposed by the United States, China has begun imposing export restrictions on a range of critical rare earth minerals and magnets. These restrictions require companies to secure special export licenses for 7 specific rare earth elements: samarium, gadolinium, terbium, dysprosium, lutetium, scandium, and yttrium, as well as magnets. Notably, these include several heavy rare earths, which are particularly crucial for defense applications and for which there is currently no significant processing capacity outside of China. The new export licensing requirements on heavy rare earths are likely to cause disruptions in supply to more than a dozen U.S. defense and aerospace companies. The impact extends beyond the military. U.S. manufacturing, particularly in the high-tech sector, faces potential shortages and production delays due to halted shipments and limited inventories. Industries relying on rare earth magnets, such as electric vehicles, could also be significantly affected. While companies like MP Materials, the only active rare earth mine in the U.S., are working to build domestic processing capabilities. Even MP Materials sends their mined REE to China for processing. The 2025 tariff exchange led MP Materials to halt shipments of its concentrates to China for processing, further complicating the situation. The vulnerabilities exposed by China's dominance in rare earths have spurred efforts in the United States and other countries to diversify supply chains and establish domestic production capabilities. In the U.S., MP Materials are investing significantly to create a full rare earth supply chain, from mining in California's Mountain Pass site to processing and magnet production in Texas. This facility represents the first U.S. domestic production of these materials in decades, with the capacity to produce 1,000 metric tons of magnets annually. The U.S. Department of Defense has also funded Lynas Rare Earth's U.S. subsidiary. Lynas completed the purchase of a 149-acre greenfield site in Seadrift, Texas. This large site will allow for co-location of heavy rare earths and light rare earth separation and processing, as well as potential future growth opportunities such as downstream processing and recycling, to create a circular mine-to-magnet supply chain. DARPA are also researching ways to secure a critical link in the domestic rare earth supply chain using a different kind of method: biomining. The Environmental Microbes as a Bioengineering Resource, or EMBER program, is a DARPA initiative to use microbial and biomolecular engineering techniques to separate and purify rare earth mixtures like the ones produced at the MP Materials Mountain Pass mine in California. The program was inspired by microbes found living in harsh volcanic environments that were using rare earth elements in order to survive. Finally, the United States also is using its geopolitical strengths to negotiate with both Greenland and Ukraine for access to their rare earth resources. Those efforts are ongoing and face varying geopolitical resistance. Japan has made significant progress in diversifying its rare earth sources, notably by investing in the Australian mining company Lynas. Australia's Lynas Rare Earths is the largest producer of separated rare earths outside of China, but still sends oxides to China for refining. Australia is expected to be reliant on China for refining until at least 2026. Without rare earth elements in the future, your phone would still work, but it might weigh more, last fewer hours, and have a dimmer, less vibrant screen. Without powerful neodymium iron boron magnets, EV motors would need heavier, less efficient materials. At home and at work, internet speeds would slow. Fiber optic cables depend on erbium amplifiers to maintain strong signals across long distances. Without them, cloud services, streaming, and global communication would degrade. Hospitals would face new challenges. MRI machines and precision surgical tools depend on rare earth magnets and phosphors. Care would become slower, diagnosis less accurate, and some treatments more expensive. Defense systems would gradually lose their technological edge. Fighter jets, missile guidance systems, and secure communications all rely on rare earths for critical performance. Thank you for watching our first video on rare earth metals. In our next video, we'll delve deeper into another fascinating topic. Make sure to subscribe so you don't miss it. Let us know your thoughts and questions in the comments below.